For record, all students are here except Brian. Brian not yet here. Okay, today we're going to look at chapter 5, which is on flow over immersed body, meaning our body, what happened to a body that we put inside a flow. Right? Today, or the keyword is that we're going to learn what is lift, what is drag, why a aircraft can fly, or why an object it will create some drag. All right. So we'll look at lift and drag for the in this week. All right. So these are the main point that we're going to go through in chapter 5. So lift and drag concept, and then inside drag we'll look at friction drag, pressure drag, and then what is the drag coefficient. Then we'll look at pressure distribution and what is the boundary layer. Right? Okay, so this is a few video. So I think this one we will play one video. Let me know if you're not able to hear. If you're not able to hear my mic or not able to see the screen. So this is the aerodynamic test in the wind tunnel. So they will turn on the wind and then they generate some lift on the surface, and then they put a smoke to go through, and then they will see what happened to the flow on the car body. Okay, this is a full-scale wind tunnel. So in our country, we have a full-scale our Proton workshop. So they have a full-scale wind tunnel there. So another way is that this is on the experimental data, with the real data. And another way we study aerodynamics or lift or drag forces is by software. So the name of software that popular is that ANSYS. It's ANSYS. So if you go to industry, if you're in the aerodynamic engineer, then most of the time you will come across ANSYS software. I think some of you will use ANSYS as your FYP, your final year projects. Okay, so we'll look at 3 types of body when we talk about flow over immersed body. So in your handout question 1, you will see 3 photos there. So the first one on the left, first diagram here, is that two-dimensional flow, two-dimensional flow, where we look at X and Y axis. It can be Y and Z, or it can be X or Z. So two-dimensional means you only look at 2 axes. And the flow is from the left to right. So this is a two-dimensional flow. And then the middle, this is asymmetric. Asymmetric, it means that if you cut across all the body, for example, you cut across plane XY, you cut into half, you will see that the top body and the bottom body, or top portion and bottom portion, is the same. All right. So in the simulation software, in asymmetric body, usually we only simulate a quarter or half of the body to save the time for simulation. So this is asymmetric, meaning what you have on the top will be same as on the bottom. The cross section will be the same. And again, the flow is from the left to right. And the more complex or more realistic example is the three-dimensional flow. This is the one that I show you. the video just now, right? That is a three-dimensional experimental test. So we have two-dimensional flow, asymmetric flow, and three-dimensional flow. So each one of it will give you different equation. The most simplest one is on the left, two-dimensional flow. You will cancel out many things in the equation. Asymmetrics, you can cancel some, but if you have when you have a three-dimensional situation, then you need to consider many things. Okay. Your coming assignment will be a three-dimensional scenario for your info. All right. Now we start to look at what is lift and drag. All right. So if you have, let me give you the diagram. All right. Now, if you look at the diagram on the screen or either in the question number 3, there's a one diagram there. So how you define lift and drag? So when you have a flow, or we call it upstream. Upstream means the flow before the body. All right. So you have an upstream from the left. It is defined as U. And if your flow, if the force, lift and drag is a force. So when your force is parallel to the upstream, we call it drag. We call it drag. Right, on the screen here is a textbook definition. Right. So if your force is parallel to the upstream direction, we will drag. So if the resultant force is normal, means 90-degree relative to the upstream, then it becomes lift. So this is a general understanding when you want to develop equation from the free body diagram. So this is a very important concept. If you mix these two up, then most of the time you'll get the wrong answer. All right, so this is the first step. Normally, when we want to solve a chapter 5 problem, so we'll look at what is your upstream direction. Then we look at the body. Then straight away we go and draw lift and drag direction component. Okay. So again, lift is perpendicular or normal to the upstream. Drag is parallel to the upstreams or in the direction. Or in the direction means parallel. Okay, so far nothing complex here. This is on the stress on. So there are a few more forces that we will consider. So one of it is pressure on the body itself. Two forces that link to the body is that one is pressure, one is shear stress. So pressure, we will use P to represent pressure in this chapter. And then shear stress, we will use tau W. W means wall, body, the body of the structure. All right. And if you look at pressure, so this is the pressure distribution. Later on, we will look into. We look into pressure distribution. Right, what happened to the front? What happened to the top? What happened to the bottom of the body later on? So, and then this is the shear stress. All right. Now, when we look at lift and drag, both of these can say 90% their equation are same. So if you look at this diagram, you will know that later on you will link your lift or drag to pressure and shear force or shear stress. All right, you'll link these two components to lift and drag later on, of course with the U, right? So pressure and shear stress. Shear stress or tau W. Tau W. So just now we cover what is type of flow, two-dimensional, asymmetric, three-dimensional, and then we look at lift and drag. What is lift? What is drag? right? And how later on we will link lift and drag to the pressure and shear stress. Okay, we were going on question 5. How the resultant of shear stress and pressure distribution can be obtained, meaning we start to derive the equation for, in this case, we will derive for, I think for lift, right? So if you look at the diagram in your question 5, you will see the same diagram on the screen. So we have X and Y axis, and then we have a surface area, which is slanted with the angle, and this angle was defined with x-axis and the normal angle of your pressure. Okay, because the pressure in this case, pressure always 90 degree to the surface. Yeah, pressure component always 90 degree, always act normal to the surface. All right, the definition for pressure in this chapter is that your pressure always act perpendicular to the surface, and the angle we will use is, we refer to, you can use, because it's perpendicular, so we know the position of your surface. We put the horizontal axis of your surface relative to the x-axis, so we get the angle here. So this angle is same with this angle. So this is the mathematics geometry equation relationship. And our flow is from the left to right. All right, from the left to right. So again, we're going to derive the equation for lift or drag by using pressure and shear stress. So we need to change this pressure and shear stress into force, because always we will convert all the stress into force in our equation, in our derivation. So how you convert pressure into force? You take your pressure times area, you get force because of the pressure. And shear stress also, you take shear stress times area. Okay. Now, if you forget the definition for force, pressure equal to force divided by area. Shear stress equal to force divided by area also. So you want to find, convert into force. So your pressure force equal pressure times area, right? So your shear force also, you take the shear stress times area. So in here, because we look at very small area, which is the height, the light, the red line here, a very small area. So we use the mathematics definition dA. So we add a dA at the back of the equation here. So P times dA, you get pressure force. Shear stress times dA, you get shear loading or shear force. Okay, so we group all the force in X and Y direction, meaning you break your pressure force and your shear stress into X and Y axis. Again, you refer to the axis that we have here. So all the force in F axis is that all the force in this direction. So again, this PdA, this is your PdA. You can break into, again, this is resultant. So you can break into x-axis and y-axis. So this component is PdA cos theta, because the theta is here. All right, theta is here. So this component is cos theta. All right, so you break your force into x and y. So we look at x first. And then your shear stress also have x and y. X, y. So your shear stress is sine theta. Okay. And then you group all the force in y-axis again, same. Your pressure force is pointing down, is opposite compared to the your reference axis y. So we get negative because it's going down. And then your shear stress is going up. Get positive. Shear wall dA cos theta. Okay, so I think you have no problem on the derivation for the forces in x direction and forces in y direction. Okay. Okay, Brian is here. Okay, so at this point, we already have all the force in x-axis and all the force in y-axis. So at this moment, we still at a very basic mathematics derivation, where we look at the pressure component and shear stress component on a small surface, and we break into x-axis and y-axis. Okay, if I go too fast, stop me a while. I can give you some times to copy the equation. All right, and from the definition for lift and drag just now, so all the force that parallel to your upstreams, to your velocity, will be drag. So your D represents drag, equal to integration of all the small force along the x-axis. So this is the mathematics definition if you want to define drag. Right, again, drag is along your upstream direction, right, x-axis. So x is d equal to integration of dx. Of course, integration dx. So you look at this equation later on, you integrate. Then another definition for lift is that we know that our lift is always perpendicular to our upstream. Is in this case is along y-axis and is pointing up. So L represent lift equal to integration of dfy. Okay, so later on I think I will not repeat all these lengthy equation later on. So when you see dx, it means this whole thing. Dy means this whole thing, and you integrate. Okay. Okay, so far, any question on these two definitions, lift and drag? Make sure you understand, because later on your assignment, you need to use this equation to explain your project. Okay, let's look at one example, which is tutorial number 6, question number 6. We try to apply what we learned just now, definition for lift and drag, and then how we derive it, how we apply it in the scenario. Now this example, again, just give you a highlight, heads up that question number 6 will be related to your assignment number 1. You have 2 assignments. So assignment number 1 will be related to this one. But detail I will brief you on this coming Friday. Now, tutorial number 6. So what does it, what we have here? So air at a standard condition flow past a flat plate. So we have a flat plate on the screen. So in case 1A, plate is parallel to the upstream. So your upstream is from the left, is parallel, position parallel. Magnitude is given also, the upstream. And number B is perpendicular to the upstream. The pressure and shear stress distribution of surface are given. So this is pressure and shear stress. So pressure component, shear stress component, and on the left, on the right here, you also have pressure, front and back. This is front, this is back, and you have a shear stress, front and back. Okay. Definition is given here. All right. Now again, just a reminder, your lift and drags will be is generated because of the effect of pressure and shear stress. All right. So we're going to use these two, pressure and shear stress, in our equation. All right, let's look at case number 1. Okay, I pull the diagram together. So we look at question, your diagram number 1, this is A. So you determine the lift and drag on the plate. So first case, we have the upstream is parallel to the plate, and the pressure again is always acting normal to the surface, right? So, and then the B is given, B is the width, 10 meter, and your velocity is 25 meter per second, pressure 0 gauge, and your shear stress were given by this equation, Newton over meter square. So again, you look at this one, Newton meter square is Pascal. So you need to convert this one into force later on. Pressure also. Length is 4 meter. So we define the angle first, right? If you compare this angle with the diagram in your question number 5, so our angle here, our angle top surface, we will have top surface and bottom surface. So top surface, your angle is 90 degree. So you know it's 90 degree. So you look at this one. So this is the top surface. This is 90 degree. We refer to the top surface. Then on the bottom surface, you have 270 degree for the bottom surface because you rotate the angle for 270 degree. So this angle is important, and you try to understand the diagram in your question number 5. Again, now this is fairly related to your assignment number 1. You understand the angle, all right, and you do your report later on. Right, this is just a reminder of how you get the angle. So our lift force with this perpendicular to the upstreams. So we have two components. One is on the top, one is on the bottom. So again, pull out the definition for lift in the mathematic form. Lift equal to integration of your y component, dfy, and then combine with the component at the bottom. Integration bottom, this is just a detonation bottom, right? So in exam or in your in your answer later on, so you can put 1 or 2, but you have to label 1 and 2 lah, right? Right. Then you continue with the mathematics equation. So we know that lift is along y-axis. Along y-axis. That's why in our integration here, we don't have shear force. We don't have shear stress component here. Okay, now your lift consists of pressure and shear stress component, but you have to depend on the angle. You have to depend on the angle. So on the top here, the shear stress is parallel to the upstream. That's why we don't have the shear force. Okay. Okay, try to understand this equation. This one, this is drag, this is lift. So because our angle is 90 degree for the top, so 90 degree, 90 degree. So for the top side, 90 degree is 1. cos 90 degrees is 0, so second component you don't have shear stress component. That's why it explains this equation. Bottom of the same, because bottom the angle is 270 degree. You substitute 270 degree into your lift equation, which is this one. You substitute your 270 for the bottom, 270, 270, right? So you only have one, you have negative because it's pointing down. The force is pointing down, negative. So be careful on the sign when you do your analysis. P is pointing down. Right, and for the bottom one, your pressure is pointing up, so it's positive component. So because we know that the pressure component is the same, so you have a negative plus positive. The A area is the same, so same magnitude, you plus and minus, you get 0. So for the parallel plates, you don't have lift component. Okay, for the lift, we don't have. For the first case, where the plate is parallel to the upstream, we don't have lift force. Okay. Now we look at what happened to the drag. Now again, drag, you pull out the equation from the definition just now. So d equal to integration of your dx. So your drag will always parallel to the upstream. So of course here we have top and bottom surface. Again, so integrate what happened to the top, dfx, plus what happened to the bottom. Right. So again, substitute these two angles back into this equation. Right. Then substitute the angle here. So for your drag, you will have d equal to integrate shear stress, dA, because we need to convert what we have on the body. Again, body, we have pressure and shear loading or shear stress. In this case, your pressure component equal to 0 because of the angle. And from the diagram, you can see the component of your pressure also perpendicular to the upstream, so we don't have drag force. Your drag always parallel to the upstream. So you have shear stress times dA, top and bottom. So both, you see, have the same magnitude and both is positive. So you will have 2 integration of shear stress times dA. So this is your drag. Okay. The rest is just substitution of what is given in the diagram. So for this moment, we already derived the equation for lift and drag. Lift always perpendicular to the upstream. Drag always parallel to the upstream. All right. We focus on the upstream rather than the surface orientation. Huh? So we always look at what is the direction of your upstream, your flow direction. Okay. Then the rest is just substitution of given equation. In this case, your stress equal to, because it's given, 1.24 times 10 negative 3 divided by square root of x. So you just substitute and then integrate. In this case, because this is in the x term, your equation is using x. So you break your dA. Your dA is is, you break into 3D. So here to here is x. You're given the width of the surface. So if you integrate 1 to dx, b dx is your dA. You take b times your dx here, dx, you get your dA. So you change your dA into 10 times dx because the width is given. The width is given. Okay, then you do the integration steps, make the mathematics. Yeah, again, a reminder, make sure you are using the correct unit. Change all the unit into unit SI before you do the calculation. All right. So at the end, if you do the calculation, the reference answer will be D drag equal to 0.992 Newton. Okay, 0.0992 Newton. So question number 6 show you how we apply the definition of lift and drag, and also what happens if you rotate your subject, your object. So we already solved for the first component, which is parallel surface. Any question for the parallel? Any question you want to ask me?
Sir,
Yes.
at the integration,
Mm,
the drag one,
drag. This one.
yeah,
Mm.
they have the 4 0, right? The 4 is the length of the component, the plate.
You mean this one, 0, 4, is it?
Yeah,
0, 4 is your dx, your x direction. Where's your x direction here, right?
yeah,
So you integrate from where? From here to here, right?
the length of the plate.
Yeah, this one.
Okay.
4. Because the integration always follow what you have at the back here. The
Yeah.
integration always follow. Yeah. So you look at diagram. So what is your x direction? So it's this one.
Okay.
Yeah. Any more question? Clear your doubt, because again, this example is related to your assignment number 1. Right? All right. So if no question, we move to the second example, second case where the plate now is normal to the upstream, and you have front pressure and back pressure. So just repeat. Important is the angle. So angle for the front is 0 degree. Angle is 0 degree. Back is 180 degree. So call out the lift definition again. So in this case, you have two. One is in the front, one is in the back. Right? It's a different scenario compared to the parallel plate just now. Now we have perpendicular to the upstream. So we have a front scenario and back scenario. Of course, you can mention there's some error here, on the top here, but this is very, very small compared to the force on the front and back. There's some force here, of course, yeah, but it's very, very small compared to the front and back. So we integrate the force in front and integrate the force at the back. Now again, no matter whether it's lift or drag, we will have force and shear stress component. It depends on the angle between the flow and the pressure or shear stress. So because the angle is degree 0 on the front, so your leaf will only have shear stress, right? Because your pressure now is parallel to the upstream, so your leaf will always perpendicular. This is V or U. Your leaf always 90 degree to the upstream or to the velocity. Your drag will always parallel to the velocity. So that's why in this case, when you calculate for the leaf, you only see the shear stress along the surface here because it's perpendicular to the upstream. Your pressure here do not generate anything as a result of the upstream direction. Why? For the back, and then for the back we have a because your shear stress here is at the back, at the back. So yeah, so this is at the back, negative. And because these two magnitude is the same, because shear component is the same in this equation. So shear front and back is the same. So your leaf equal to 0 Newton. You don't need to go for further analysis because you know that from the definition from the diagram, these two components are the same. So positive component minus negative component, you get 0. Then you go for the drag also. Drag will be integration of what happened in the front, dy, plus what is happened to the back, dy. Okay. Again, your force, this is upstream. So what component parallel to the upstream will become drag? What component that perpendicular to the upstream will become your leaf? So we're now looking at drag, right? Let me see. Okay, so I think there's a typo error here. This is not dy, it's dx. This is dx. All right, typo error on the screen. So d equal to integration of dx fx because drag is parallel to the upstream direction. So again, when you use these slides later on, there's a typo error. This one. So d equal to integration of front PdA. If you substitute the angle inside the equation just now, front is 0 degree, back is 180 degree. Okay. Then you only have pressure component for the drag. So you're given what is in the front, what is in the back. So your front, P, given in the diagram, P pressure in the front is 0.744 times 1 minus y squared divided by 4 is the front. So you substitute this one in, and you have a negative. This one is P negative 0.893. So you just follow negative 0.83. Actually, at the end, you still get positive. What you need to be careful is the integration here, because this is a, can say as a symmetry plate. So that our plate length is same. Our plate length is 4 meters just now. And we refer to the center of the plate. So this is 0. So you know that the length is 4. So on the top maximum you have 2. So at the bottom you have -2. So you're integrating from the center, meaning you in the mathematic form, you integrate from -2 to 2. So this is also need to take note, because our flow here is parabolic. And it will be wrong if you use t equal to integration 0 to 4. Then you will get the wrong answer, because this equation here, parabolic equation here, is starting from the center. Right, so if you integrate 0 to 4, then you get the wrong answer. So be careful. Yeah, remark for the integration component, drag, you integrate from 2 to -2 rather than 0 to 4. So be careful, especially when it comes to your final exam. These are some trap. Most students, when it comes to exam, they will forget. So the rest is just mathematics calculation. You do the analysis at the end, you'll get 5.6 Newton. Okay, so at this point, at least you should know that in general concept, you should know that what is drag, what is lift, by looking at the direction of the upstream. And then you know that your lift and drag consists of two main forces. One is consists of pressure, one it consists of your shear stress. Right? And the derivation come from this diagram. From this diagram, which is in your question number 5. So try to understand the setting, the surface orientation, the angle. Then you're able to answer any question in this chapter. As long as you know what is 0 degree, what happens if you have 0 degree, what happens if you have 180 degree, so what happens if you have 90 degree, what happens if your degree become 270 degree. Okay, now spend some time to study this diagram and the equation that you derived just now, because it will help you to answer what is lift, what is drag. So if you confuse in this diagram, then later on you will miss out what is drag, what is lift, right? Let me do correction. This is Excel. This is what. Okay, any question so far for question 6? Okay, if no, then let me stop the recording.